Start recording here. Okay, well, hello and good morning, and I hope you guys are all doing well. Happy Friday to you all. In the other class, I posted this link in the chat, and I'm going to do the same. Today we lost a musical legend, Bill Withers. Bill Withers died, and he played. He has some great songs, "Lean on Me" and things like that. But one of my favorites, and something that we should all listen to, is "Lovely Day." So you know, I would play it for you guys right now, but I think if I do, I would get a copyright strike against me on YouTube, and then and also the you know, while Zoom is great for speech, it's not great for streaming music. So you know, trying to stream music over Zoom would do a great injustice to the song. So, but anyway, I've posted a link in the chat, and I'll probably post this up on CCLE also. As part of your homework this weekend is to listen to music by Bill Withers, cheer you up, but also just to remember his legacy. All right, let me start sharing my screen here, and let's go there. And so today we are going to look at OLS matrix notation. I did not get to cross-validation last lecture, and I don't anticipate getting there today. So my aim is to kind of hit the same benchmarks for both lectures to stay consistent between the two classes. And so this is where we left off on Wednesday. On Wednesday, we talked about ordinary least squares, and then and we talked about finding the gradient. And I said the gradient is sort of similar to the derivative, except it's multivariate, right? We are you know, our data often exists in more than one dimension, but our loss function, you know, when we talk about the sum of squared residuals, that value, that output, is a single scalar value, all right? And so here, these are all functions. F returns a scalar value, but the input is a vector, or you know, possibly even a matrix. But the important thing is that when you take the gradient, find the gradient of a function with respect to some vector, the gradient will always have the same dimensions as the input vector. So here, if we're talking about the least squares function, okay, or total sum of squares, or the mean squared error, that returns a scalar. But these are also other functions here, and so you can imagine some matrix, some vector x, maybe x is in 2 dimensions, and some weight matrix, also 2 dimensions. And so W might be 2 by 1, so W transpose is 1 by 2, and X is 2 by 1, okay? And so when you take the derivative, or gradient of this function with respect to W, which is 2 by 1, the output also has to be 2 by 1. If W is 4 by 1, then the gradient of F with respect to W also has to be 4 by 1, okay? And so the gradient of W transpose X is X. The gradient of X transpose W is also X, okay? If W is, say, 4 by 1, okay, we've got 1 by 4 times a 4 by 1 here, and the gradient will be 4 by 1. Here, X transpose is 1 by 4, W is 4 by 1, and the gradient with respect to W is X, which is going to be 4 by 1. W transpose W, the gradient with respect to W is going to be 2W, and when you have W transpose times some matrix C times W, the gradient with respect to that is going to be 2 times that matrix C times W, okay? So these are, and C will have to be a square matrix, okay? An n by n square matrix, okay? All right, and on Wednesday, we said, let's look at the loss function, which is the mean squared error loss function, and we wrote it in matrix notation. So we spent a little bit of time on Wednesday writing the loss function, the mean squared error, in matrix notation. And the reason why we did this was we avoided any kind of summation signs by using matrix notation. So, so if you think of kind of the sum of squared residuals, which would be kind of your y minus y hat, or in this case, t minus what f predicts, in matrix notation, we can write it this way: t transpose t, okay, 1 over n times t transpose t, minus 2 over n w transpose x transpose t, plus 1 over n w transpose x w, okay? So this is what we have. This is our loss function. And what we want to do in order to minimize our loss function is we are going to take the gradient of L with respect to W. We're going to set that gradient equal to 0 and then solve for W, okay? And on Wednesday, or I think in 100B, you guys had to do this with partial derivatives. And today we are going to do it in matrix notation. And so, so here we are going to take the gradient of this loss function with respect to our vector W, okay? And so the loss function is a scalar. W, in our case, is a 2×1 vector. And so the gradient will also be a 2×1 vector. The gradient of a function has to have the same dimensions, okay, as the input vector. All right, so if we look at this first term, which is 1 over n t transpose t, we ask, how does this vary with respect to W? Okay, how does this vary with respect to W? And it doesn't, okay? This is effectively a constant term. It doesn't vary with respect to W, and so the gradient of that is going to be the 0 vector, okay? It's going to vary 0. Again, but it has to have the same dimensions as W, so it's going to be a 2×1 0 matrix or 0 vector. Okay, here I have minus 2 over n W transpose x transpose t. How does this thing vary with respect to W? Okay, well, the scalar value just comes down. That's a scalar constant there. But if we look at W transpose x transpose t is pretty much a vector there. Okay, and if we look back to this page, we're basically looking at this top relationship. How it varies with respect to W is just going to be, you know, what we're multiplying W transpose against. And so this will vary by x transpose t here, okay? And just to kind of ensure that this is also a 2×1, x transpose has the dimensions 2×n, t has the dimensions n×1, and when we multiply that, we're going to get a 2×1. Here I've got 1 over n W transpose x times W, okay? So this quantity, W transpose x W, is pretty much this thing. We've got W transpose times some matrix C times W, okay? W transpose times some matrix C times W, and the gradient of that with respect to W is going to be 2 times C times W, all right? And so basically that's what I have here, okay? W transpose x W will become 2 times x transpose x W, right? Here I had a 1 over n term, so this becomes 2 over n times x transpose x W. And then so I can get rid of the 0 vector, and this becomes, if I check the dimensions, this is 2×1, and this is also 2×1. All right. Okay, so I know this is a lot to start your morning off with. I don't know if you guys were ready to just get into some vector calculus or vector derivatives right away, but here we are. And I just want to take a moment, make sure everybody's following along. So if this is okay with you guys, give me a little green check mark in your feedback icons. And if this is not okay with you, please give me a red X or some other feedback icon here. All right, okay, so 27 of you have given me green check marks. We got 48 in the room, so so the other 20 of you, you have not responded, so I hope you guys are there and following along, and don't hesitate to throw a question into the the group chat, or or give me a different feedback icon to let me know something isn't making sense. Okay, and again, to get the feedback icons, pull up the participants panel. So click the little participants button, and that should bring that up, where you can also raise your hand and things like that. Okay, and also pull up the chat so you can see ask questions there. Okay, and so the next step that we're going to do is that, so we have taken this gradient with respect to W, and what we want to do is we're going to set this gradient equal to 0, and we're going to solve for W. Okay, so here I take that gradient, which is negative 2 over n x transpose t plus 2 over n x transpose x w. I'm going to take that gradient, I'm going to set that equal to 0. This is the 0 vector because this has to be 2 by 1. So this is a 2 by 1 0 vector. And we are going to solve for W. So I'm going to basically, I've got a negative sign here, so I'm going to add this to both sides, and I'm going to multiply both sides by n over 2. And so the next step is going to be x transpose t, and we have is equal to x transpose x W. Okay, and to get rid of this, what we want to do is we want to isolate W by itself. So we want to kind of get rid of this x transpose x over here. And in matrices, you are not allowed, there's no such thing as matrix division. You cannot divide by a matrix. But what you can do is you can multiply by the inverse of a matrix. Okay, so we've got x transpose x, and so we can multiply both sides by the inverse of x transpose x. I can do x transpose x, and I can multiply that by x transpose x inverse. Okay, so so that's what I'm going to do. Okay, and I multiply both sides by x transpose x inverse. Okay, now you might wonder, do I do x transpose t times x transpose x inverse, or do I have to go x transpose x inverse times x transpose t? Because remember, with matrix multiplication, the order in which you multiply things matters. You cannot A times matrix matrix B is not going to be the same as matrix B times matrix A if the dimensions don't line up. Okay, and so again, to kind of guide you with this, it's always helpful to write the dimensions of each term underneath your thing. So x transpose x, x transpose is going to be 2 by n, x is n by 2, and so x transpose x is 2 by 2, and the inverse of a 2 by 2 matrix is also 2 by 2. Okay, and so this quantity here is a 2 by 2 matrix, and I want to multiply it by x transpose t, which is going to be 2 by 1. Okay, x transpose is 2 by n, t is n by 1. And so the only place I can put it is in front. If I try to put it after, I would basically, x transpose t is 2 by 1, and I'd be trying to multiply a 2 by 1 matrix by a 2 by 2 matrix, and those dimensions will not align, and I would get a dimension mismatch. Okay, so here I would multiply by the front. Okay, and so I have x transpose x inverse times x transpose t. Over here on the right hand side, I have x transpose x inverse multiplied by x transpose x. Okay, so this matrix x transpose x will cancel out the when I multiply x transpose x inverse times x transpose x, they would multiply into the identity matrix. Okay, which is basically the matrix equivalent of a 1. So that will give me the identity matrix, and that will give me that will leave me with W, identity matrix times W. And so we'd have x transpose x inverse x transpose t is equal to W. So the value of W that will minimize my loss function here, okay, is going to be this, x transpose x inverse x transpose t. Okay, and so this is going to be an important relationship. You will see this almost certainly in your 100C class when you start dealing in matrix notation. Okay, and that's what we have here. So the solution for ordinary least squares regression okay, that will minimize the loss function is, we take this, we take the gradient of this with respect to W, we set that gradient equal to 0, we solve for W, and this is the solution where we arrive. Okay, so that is going to be my estimates for W hat. All right, so what I'm going to do now is I'm going to just show you how what this would look like if we were to do such a thing in R. And so here I've got just a very, very simple toy data set. My X values are 1, 2, 3, 4, and my T values are 1, 3, 2, 4, 1, 3, 2, 4. So it's not a perfect straight line. We've got just a tiny bit of scatter, and that will affect that we can try to use this to figure out what my slope and intercept should be, okay? So my X matrix will be produced by binding a column of 1s to my column of X values, okay? So X is the values 1, 2, 3, 4, and I also attach a column of 1s, okay? And now that I've got this n by 2 matrix, or a 4 by 2 matrix, I can do X transpose X, okay? X transpose X is going to give me a 2 by 2 matrix, okay? So the transpose operation in R is T, is the function T. So X transpose times X is this 2 by 2 matrix. The inverse operator, okay, to take the matrix inverse in R, you're going to use this function solve, okay? Solve applied to a matrix will find the matrix inverse, okay? So the inverse of the 2 by 2 matrix X transpose X is going to be this 2 by 2 matrix, okay? And then the next thing I'm going to do is I'm going to multiply X transpose X inverse by X transpose. And when I do that, I'm going to get a 2 by 4 matrix, okay? And then lastly, if I do X transpose X inverse times X transpose times the values T, which is kind of my column of actual observed values for T, this will give me W hat, okay? And this results in a 2 by 1 matrix, and these are the estimates of W, that is my slope and intercept, or intercept and slope, I should say. These are the estimates of the intercept and slope that will minimize the loss function, okay? The loss function being the mean squared error. And so we say the estimate for the intercept is 0.5, and the estimate for the slope is 0.8. All right, and that is based on our observed values of 1, 2, 3, 4 paired with 1, 3, 2, 4. Okay, if I were to fit a linear model using R's LM function, that is predict T based on the input values X, I get the same values. I get my estimate of the intercept is 0.5, and my estimate of the slope is 0.8. Okay, which is no surprise because this function here, X transpose X inverse times X transpose T, is the values that we said will minimize the ordinary least squares loss function. And LM is using the same loss function there to minimize, and so it uses this. It doesn't use matrix operations on the in the internals, but it is minimizing the same loss function, and so that is what we get. If we want to get predicted values, okay, if we want to get predicted values, we are going to take our input matrix X, okay, whatever input matrix X is, and you multiply it by your parameter estimates, W hat. So we have estimated the slope and intercept. Okay, the slope and intercept, or intercept and slope, is estimated to be 0.5 and 0.8. And we can take some input matrix X, which has a column of 1s and column of X values to make predictions for. And when I multiply that, this is going to give me my predicted values T hat. Okay, so for the 4 values that I have, and I input this, I'm going to get T hat 1.3, 2.1, 2.9, and 3.7. Okay, and if I were to kind of plot my predictions, this would be the fitted line here. Okay. All right, so this is where we are. Let's take a look at the Olympic data, okay? So we can do the same thing with the Olympic data, all right? So in the Olympic data, we're looking at data from the Olympics, I think, starting in 1896, going up to around 2012 in our data, okay? And we're looking at the 100 meters, 100 meter dash gold medal times. And we can see that, you know, as time progresses, the times seem to get faster, okay? If we just use LM using R's linear model function, LM function, we're going to get the coefficients, the intercept to be 36.309, and the slope to be negative 0.01328. Okay, basically saying every year that goes by, our prediction for the gold medal time would drop by about 1/100th of a second, and I guess every 4 years, about every interval for the Olympics, our prediction drops by, you know, close around 5/10ths of a second, 5/100ths of a second. I'm sorry, 5/100th of a second, 0.05 ish, something around there. Okay, and so here I can create my X matrix by taking the column of years, our input X, and I'm going to bind it with a column of ones. Okay, so I'm going to get this column of ones and the column of X's. And this is what I have. And I'm going to go ahead and just do X transpose X inverse. Okay, that's what I have, X transpose X inverse by throwing it in solve, multiplied by X transpose times, this time my actual values, my T, the observed actual values, are in this column. I'm going to take Olympic $ time, throw it into a matrix, and I can do this, right? Because these are, what we're trying to do is we're trying to minimize the difference between these observed values and what we are predicting, okay? And we get W hat to have an intercept of 36.309 and the slope for X to be negative 0.013275, okay? And if I go back to my linear model estimates, indeed, we get 36.309 and my slope to be negative 0.01328, and that's just because R has rounded it off to fit the that printout there. Okay, so we get the same exact values using LM or our matrix operations. When we are making predictions, okay, my T hat says will be found by taking the input values X and multiplying it by our predicted values W hat. Okay, so we're going to do X times W hat, and that's going to give us our predicted values T hat, okay? And so here are our predicted times, 11.139, 11.086, and we can see that as each year goes by, the predicted time for the Olympic gold medal time drops by a little bit, okay? Close to 0.05 here. And so, so we can see this going down, forming a straight line there. Okay, how are we feeling? We're feeling okay? All right, okay, thank you for that, that thumbs up, and thank you for your green check marks here. Okay, all right, so what we are going to do now is we are going to see if we can get a non-linear response from our linear model, okay? So when we talk about linear regression, multiple linear regression, we are not saying that everything when we predict has to be a perfect straight line. That's not what we are saying. We are saying that the relationship between Y, the output, and our inputs X are linear, okay? As in that the relationship is linear, meaning there's a constant, whenever one of those things changes, it has a constant impact on the output. But the input terms themselves might not be linear, okay? So here is our Olympic data, and what we're gonna look at is we're gonna say, well, earlier I fit a straight line model, but maybe a quadratic model is a better fit. Maybe a higher order polynomial is a better fit. These are questions that we might have. So when we are working in matrix notation, I can do this by expanding my X matrix. So right now, or on the previous slides, X was an n by 2 matrix, okay? I can make this accommodate a quadratic term by expanding it, adding a third column for X squared. So X is going to be an n by 3 matrix. I've got a column of ones, I've got the column of X values, and now I'm going to add a column of X squared values, okay? So X is going to be n, and now I've got 3 columns, okay? Column of ones for the intercept, column of x's for the linear term, and a column of x squareds for the quadratic term. And this is what it will look like for the Olympic data, okay? Here's my column of ones, here's my column of x. This is the year in which the Olympics were held. And this is the column of x squared values. Oh, thank you, Yanhua, for the reminder for what is the first answer to the quiz. The first answer to the quiz is going to be A as in apple. First answer to the quiz is A as in apple, all right? A as in apple, first answer for the quiz. Okay, so this is our x squared terms. And we can see when we take x and we square them, we're going to get very big values, right? 1900 squared is 3,610,000, okay? And we want to see, you know, is there a relationship using kind of the x squared term? So we're going to take x 1900 and square it, we get 3,610,000, but we're asking, is there kind of a quadratic relationship somewhere in there? All right, when we have the intercept and the linear x term and the quadratic x term, you know, our predicted values are going to be w0 plus w1 times xn plus w2 times xn squared, okay? And so this is what it looks like when we write it out, but we can express this thing in matrix notation using this, W transpose xn. So imagine W being a 3 by 1 matrix, okay? So W transpose will be 1 by 3, and xn will basically be this row of, or as a column, okay, of the 1, the xn, and the xn squared, okay? And so our predicted values is going to be W transpose xn, okay? And so when we were thinking of our linear model with only, without the quadratic term, it was also, you know, your predicted value was also W transpose xn. Okay, and so the column matrix of predicted values, okay, can be expressed as just taking the matrix X multiplied by W. So the matrix X, again, is n by 3. W is now a 3 by 1 column matrix, you know, with terms W0, W1, and W2. And the predicted values is going to be this one single column where we have multiplied X times W. Okay, so this is n by 3, this is 3 by 1. This is going to be an n by 1 column matrix of predicted values. And that matches exactly what we want. So if this is our predicted values, then what happens is that my loss function in matrix notation remains exactly the same, okay? So on Wednesday, we worked out that the loss function in matrix notation can be written as T minus XW transpose T minus XW, okay? So because my predicted values is given by the same matrix operation, matrix X times W, the loss function in matrix notation remains exactly the same. Inside, X has changed from an n by 2 matrix to an n by 3 matrix, and W has changed from a 2 by 1 matrix to a 3 by 1 matrix. So those things have changed, but as far as how we write the values in matrix notation, that has not changed, okay? And so we can see that there are advantages to using matrix notation, whereas before, if we've been using this in an expanded form, you know, writing out the loss function would have so many more terms, okay? So many more terms. Instead of just having, you know, y minus the intercept plus the slope times x, and take that difference and square it, we would now have y minus intercept plus slope times x plus the other coefficient times x squared, and then thing. So you'd have 4 terms in there, and you'd square that, and we could see that would get much bigger. Okay, matrix notation keeps these things a lot simpler. Okay, and because this is exactly the same, we could use the same steps for solving W that will minimize our loss function, and we would arrive at the same exact solution of W hat being X transpose X inverse X transpose T. Okay, so whereas if we were to have written it out with partial derivatives, we would have to solve 3 simultaneous equations, right? We would have the partial derivative with respect to W0, we set that equal to 0. We have the partial derivative with respect to W1, we would set that equal to 0, and we'd have the partial derivative with respect to W2, and we would have to set that equal to 0, and we would have to solve for where all of these things equal 0. So, you know, in the beginning, it might have felt more comfortable to use partial derivatives, but there are significant advantages to using matrix notation and doing, you know, vector derivatives and, you know, just the touch of vector calculus. And we will see that our solution remains the same. W hat is X transpose X inverse X transpose T. It's just that our dimensions of X are now n by 3, and T is now, you know, no, T is still n by 1, but our dimensions of X is n by 3, and W hat is 3 by 1, okay? Is that all right with you guys? Okay, great, thank you. Thank you guys for those of you who are saying yes and letting me know. Okay, but what is going on here is if I try in the next step, I say, okay, well, you know, here earlier, right, back here on slide 23, I created my X matrix. I took my column of 1s, I took my column of X's, and then I took X squared, and I did that. And so X is a big matrix that's n by 3. And when I say, well, let's do this, X transpose X inverse times X transpose times T, R gives me an error. R gives me an error. So what happened? Why is R giving me an error? We just went through and I said, hey, everything's going to work out to be the same as before, but now R is giving me an error, okay? And it says error in solve X transpose X, solve X transpose X, okay? So it's saying when it's trying to find the inverse of this thing, it says system is computationally singular, and there's like more stuff here, okay? But it's giving me an error, all right? And what is going on is that when you look at this matrix, X transpose X, some of our answers are coming out really, really, really big, okay? So what's going on is back here, here when I squared X, I got something on the order of 3,610,000, okay? And when I take this matrix, this n by 3 matrix, and I do X transpose X, that last column, 3,610,000. So basically something on the order of 4 million, okay? Actually, for the year 2000, 2000 squared is 4 million. When I take 4 million, and if I multiply that by another 4 million, I'm gonna get 16 trillion, okay? 16 followed by 12 zeros. And when you sum all of that up, we're getting something on the order 4 times 10 to the 14. We're getting some really, really, really big numbers, okay? And when you have a really big number and you ask X, and you ask R to find the inverse of this matrix, X transpose X, where one of your terms is on the order of 4 times 10 to the 14, when you ask for the inverse, it's going to produce some extremely small values, you know, 1 over the determinant, okay? So I don't know if you guys remember how to take the inverse of a matrix, okay? And I think it's a reasonable thing to ask you guys to be able to take the inverse of a 2 by 2 matrix, okay? You know, for exams and stuff, be ready to take the inverse of a 2 by 2 matrix. I will not ask you guys to invert a 3 by 3 matrix or anything bigger than a 2 by 2 matrix, but I think it's reasonable to ask you guys to take the inverse of a 2 by 2 matrix. But anyway, what's going on is because this term is so big on the scale of 10 to the 14, when we try to calculate the inverse, we are running up against the limitations of floating point arithmetic, okay? So in 102A, I spent some time talking about how, you know, the computer has this machine epsilon, which is on the, you know, 2 to the negative 52. We have 52 bits to express the mantissa, and so we can't express, you know, the difference between two adjacent numbers, anything smaller than 2 to the negative 52, which is on the order of 10 to the negative 16. And when we are taking the inverse of this matrix, we're running to values smaller than that machine epsilon, and it causes R to get confused, okay? And so R throws in an error, and R says that the matrix inverse doesn't exist. It says the matrix is computationally singular, which is another way of saying that the inverse doesn't exist. That's not true, okay? The matrix inverse does exist. It's just that we would have to be using real numbers. Real numbers, we have no problem expressing tiny things, but on the computer, we're not able to express these tiny things. So these are problems that we run into when we're doing math and arithmetic on the computer, okay? So one thing we can do, one workaround, is we can just say, well, you know what, I don't have to work in terms of, you know, 3,610,000. What if I just divide everything or multiply everything by 0.0001? Okay, this is just an arbitrary number, an arbitrary scaling factor I've decided to use on this x squared term. So rather than 3,600,000, that has been reduced to 361. Okay, and so I called this matrix x scaled, x underscore sc for x scaled, to just indicate that I've taken the third column and I've scaled it to be something much smaller, okay? You could pick a different value. It doesn't have to be this term. I'm just trying to get it away from being numbers as big as 3 or 4 million, okay? And now, when I ask R to find W hat using this operation, X transpose X inverse, X transpose T, okay? It works, okay? It has no problem finding the inverse of this matrix, which is, you know, has values that are much more reasonable in size. So it's able to invert that matrix. It's able to multiply it by X transpose, and it's able to multiply it by T, and it gives me coefficients such as 396.328 and negative 0.3382 and 0.944, okay? And let me just show you, if I take this X scaled matrix and I ask R to calculate the linear model coefficients using LM, okay, so this would be our quadratic model. I'm going to say LM, predict Olympic time based on the matrix X scaled, okay. I throw in a +0 here, or a 0 plus, so that it doesn't fit a coefficient because I already have a column for the coefficients. It gives me the exact same coefficients, 396, negative 0.38, and 0.944. Okay, so these coefficients remain exactly the same. Okay, I just want to kind of pause here, let you guys ask any questions if you have any, or let me know if anything is not making sense, or you can give me feedback that this is all good and you have no questions or anything like that. So if you have any questions. Can I explain adding the 0 again? Okay, yes. So back here, in my X scaled matrix, I have a column of 1s, okay? This column of 1s is used so that when I multiply it by the matrix W, my coefficients, I have a W0 term for the intercept, okay? And so I'm asking R using LM to find basically the coefficients that correspond to each column in this matrix, okay? By default, R will also try to fit a coefficient, an intercept term, okay? But because I already have a column of 1s, I don't need R to calculate a separate intercept term. I only needed to calculate a coefficient for that first column, which is the intercept term, okay? So I'm adding a 0 here. If I didn't have this column of 1s, then I would leave out the 0 plus, and R would fit in an intercepts term, and then a coefficient for each of the columns in my X matrix. Okay. One thing to note is that, when you make predictions now, when you make predictions using this, your predictions have to be in the same, kind of the same format as your X. So here I scaled my X squared column, and so if you were to make predictions for other values, you would have your column for the year, and you would also have to, you would square it, and you'd also have to scale it down so that things are in the same term. Okay. So here it says, with the resulting W hat matrix, we can see what values our model predicts for each observation by just doing the same thing, X times W hat. Okay, so I've got X scaled, multiply that by W hat. I get these predicted values, 11.322, 11.228, 11.136, so on and so forth. Okay, so these are the values that I'm getting. And if I plot those, I get this quadratic fit. So this is going to be the quadratic fit to our data here. Okay. Okay. One thing that we could do. All right. So what I did to create my to do my polynomial fit is I manually kind of created this matrix, the column of ones, the column of x's, and then I took x and I squared it, but I ran into computational problems. So I took that squared value and I scaled it down by 0.001, okay? Now what R can do for us is that it can create a matrix for us using this function polynomial, okay? And when I take my values x, which is the Olympic year data, so 1896, 1900, 1904, so on and so forth, and I say create a poly matrix, okay? It creates this thing, okay? This first column is a linear term, and the second column is a quadratic term, okay? It looks nothing like the values 1896, 1900, 1904, and looks nothing like the values 1896 squared, 1900 squared, and so on and so forth. But all it's doing is it is taking these values and it is just either shifting them down, it's adding a constant, or multiplying it by a constant, okay? And we know that adding a constant or multiplying a constant to our x terms will not affect the correlation, right? Changing from inches to centimeters doesn't affect the correlation. Sure, it will change the coefficient values, but the predicted values will remain the same and the correlation will remain the same, okay? And so R will do this for us, and it will automatically kind of shift and scale things. It will also produce polynomial terms that are uncorrelated, which will help kind of, your VIF factors and stuff like that. And so R can do this. And the important thing that I want you to note, okay, is that here, when I fit the LM, I'm going to do time tilde x poly. I don't need to add a 0 plus because I don't have a column of ones here. So here it's got, a coefficient for the first column in x poly, a coefficient for the second column in x poly, and then it predicts its own separate intercept term. Okay, I don't need, because I don't have that column of ones here. Okay, but the important thing is that when you look at the fitted values here, they match exactly the fitted values we got when we manually created our quadratic matrix X and found the quadratic fit. So the quadratic fit here, we predicted 11.3229, 11.2282, 11.1366, okay? And when I find the predicted values after using R's polynomial function, I have the same thing. 11.3229, 11.2282, 11.1366, okay? So the quadratic polynomial here that I've produced by doing poly x degree 2 gives me the same predicted values. Even though my coefficient estimates are way different, okay? My coefficient estimates are way different, the predicted values are the same, okay? And again, it's kind of just like changing your units into these arbitrary units that R has decided on, but the predicted values remain the same. Okay. And so what we can do is we can say, well, that's a linear fit, that's a quadratic fit. What if I fit other polynomials, polynomials of degree 3, polynomials of degree 4, or degree 5, or degree 6? What would our function look like? So here I'm just fitting LM, using LM to fit a third order polynomial, a fourth order, fifth order, and sixth order polynomial. And R is saving me a lot of time. I don't have to bind all of these, create my matrices myself. I don't have to create a column of ones, column of x values, x squared, x to the third, x to the fourth, x to the fifth. I don't have to create these giant matrices and then have the computer try to find the inverse of a 6x6 matrix, which would be a nightmare to do. Can you imagine trying to find the inverse of a 6x6 matrix by hand? I mean, the computer would be able to do it, but it's still very computationally expensive. So R is saving us a lot of time by just running poly for us, and we're getting these different linear model fits, okay? And I'm going to graph all of these predicted lines. The linear one will be in red, quadratic in orange, and I'm going to go green, blue, purple, dark gray, and it looks pretty, okay? So I've got the straight line fit is red, the quadratic fit is in orange, and then the higher order terms are in different colors, okay? And so we can look at this and we go, ooh, that's pretty, but we're not, the point is not that we're trying to make pretty graphs, but what we want is we want to know which model is the model that I should use. How do we go about picking the best model, okay? So you guys all took 101A, right? And so what would you say, how would you decide to pick the best model between these things? What are things that you might look at? Oh, it's 11:49. Okay, let me give you, while you guys are thinking of that, let me give you the answer to the second quiz question. The second quiz question, the answer is B as in boy. Second quiz question, the answer is B as in boy. Okay, so we can look at, okay, so diagnostic plots is useful in helping us see if we have violated any of our model model assumptions, right? So in linear models, you are assuming constant variance of errors. So diagnostic plots are good for helping us decide if we have violated any assumptions, okay? But yeah, as far as deciding which model we should look at, okay, we can look at AIC, adjusted R squared, MSE. So these are things that we can look at, okay? So one thing you don't want to, well, okay, so R squared is great, but R squared will always keep going up, and adjusted R squared in general also keeps going up as if you keep adding more terms. So here is the summary table, okay? So one thing you can do is you can look at the summary table in R for your model, and here we see, okay, the linear term is significant, the second order term is significant, the third order term is significant. Okay, we get all these star values, the p-values are all small there, okay? And my R squared value is 0.8973, okay? If I look at the sixth order polynomial, okay, the sixth order polynomial, my R squared value keeps going up to 0.9233, all right? And so if you just look at R squared, you know, it's almost going to always favor kind of the more complicated models, right? And so you have other things, right? Like AIC and BIC, which applies some penalties for having too many terms, too many predictors in your model, and it kind of adjusts for that. And so your AIC or BIC values might also indicate that, okay, maybe you don't need a sixth order polynomial. Okay, maybe a third order polynomial is better, right? Other things is you would also have to just kind of think about, does it make sense that the winning race time has a sixth order polynomial relationship with the year that the race was held? And you go, well, I don't even know what it means to have a sixth order relationship with the year that the race was held. I can't think in sixth order polynomial terms. So I have no idea, right? You know, your regular old expertise on foot race progress in human history. I have no idea. So so this is tough. Okay. These are tools that we have in our toolkit, and we can look at AIC and BIC, okay? But one thing we're gonna look at, and I'm gonna save this for Monday, is we are going to look at cross-validation, okay? So on Monday, we'll take a look at cross-validation, and this will be a tool that we can use for helping us decide which of these models is going to be the best model to use. Okay, that will end our lecture for today. So let me stop our recording. Where's my, I'm gonna stop.